We begin this lecture with a first order circuit that contains an operational amplifier. So this is our operational amplifier. This is where we collect the output data. Minus plus. This means just kilo ohms. Okay. And here we have our dynamic element, an Amplifier capacitor. 8 volts, 4K, 4K, DC, and the capacitance is 3 microfarads. So we're given the following information. The magnitude of saturation voltages are 16 volts, okay. So positive saturation voltage is 16, negative saturation voltage is minus 16. And initial conditions are 0. The out is also 0. The question is the capacitor voltage. Find the capacitor voltage and the output voltage of the operational amplifier for t greater than or equal to 0. Okay. So let's obtain certain equations that we will require for our analysis. Then we can determine what region the op-amp is initially in, and then from that point on we can use our equations to obtain the result. Okay. So let's write down an equation here to obtain the differential equation that determines the evolution of the capacitor voltage. Okay, by KCL we have EC minus 8 over 4K. So we're talking about this current. Then we have this current, and we have the capacitor current that sum must equal to 0. Plus the capacitor current 3 10 to the minus 6 dEC plus EC minus ER over the resistance in between, which is 4K. Okay, equals 0. Note that the differential equation depends on the output voltage of the op-amp. Okay, not only the capacitor voltage. So if you reorganize the terms, replace K with 1000 and mu with 10 to the minus 6. This is what we have: dEC plus 500 over 3 dEC equals 250 over 3 V0 plus 8. Okay, so this is the differential equation describing VCT. What else? Let's also obtain V plus and V minus voltages, okay? So that we can use them in our analysis, and also to determine what region the op-amp is operating at. So V plus equals, this is V plus. Remember that there is no current escaping into the op-amp. We're working with the ideal op-amp model. So therefore, this pair of resistors act as a voltage divider. So 2 over 2 plus 6 times V out is what V plus is. Okay, so the 1/4 of V out appears at V plus. V out over 4. And as for V minus, this node voltage equals the voltage of the capacitor VC. Now that, to obtaining those relations, we didn't make any assumptions on the region of the operational amplifier. Therefore, they are valid at all regions. Okay, so let's begin our analysis. But for that, we have to determine what region the op-amp, in what region the op-amp is initially in. So initially, the output voltage is 0, so clearly it's for less than 16, its magnitude hence the operational amplifier is in linear region. Okay, that's where we start. There's no guarantee that we will remain in linear region for all times, but initially we are in linear region. Okay, so what we do is, in linear region, V plus equals V minus, provided that the output remains, the magnitude of the output remains less than 16. And then this will give us an expression of V out in terms of VC. We can plug that into the differential equation 1, and differential equation 1 then becomes in terms of VC only. And we have the differential equation, we have the initial condition, we will obtain the solution, okay, VCT. And then we obtain the solution, and V out is 4 times VCT in linear region, and that will give us whether the op-amp remains in linear region for all times, or if it doesn't, when it leaves the linear region and enters one of the set regions. Okay, so let's begin our analysis. Since the op-amp is in linear region, we have V plus equals V minus, and we have to have that the magnitude of the output must be less than 16. Okay, so V plus equals V minus implies here we have V plus, here we have V minus. That gives us a linear relation between the output voltage and the capacitor voltage. Okay, V out equals 4 times VC. And then you take this expression of V out in terms of VC, you put it in equation 1, and you have dVC plus 500 over 3 VC plus, equals 250 over 3. And V out is 4 VC, at least for a while, plus 8. Okay, so this is our differential equation for VC. Reorganizing the terms yields dVC minus 500 over 3 VC equals 2000 over 3. A first order differential equation, non-homogeneous, with a constant right hand side. Now that natural frequency is positive, okay, it's at plus 500 over 3. That's because we are dealing with an active component, namely op-amp. So it's easy to write the solution of this equation. We have the differential equation, we have the initial condition, which is 0, so that yields VCT equals minus 4 plus 4e to the 500 over 3 T volts. Okay. And once you have capacitor voltage, output voltage is simply 4 times that. E out T equals minus 16 plus 16 E to be 500 over 3 T volts. Okay, now this clearly doesn't hold forever, because if you look at the output voltage, it initially it's at 0. Okay, and what's happening is this term becomes larger and larger, and it grows exponentially fast. So very soon VLT will go, well, VLT is tending to go to infinity, so that means very soon it will hit the border. Okay, that is, it will hit the border 16 volts, at which point it must leave the linear region. And once it leaves the linear region, we have to reconsider the situation. Okay, because once it leaves the linear region, the output no longer, no longer can equal 4 VC. Okay, so and that changes the differential equation. Okay, so therefore these two equations hold for time between 0 and Ts, and Ts is the time at which op-amp leaves linear region, and that we have to figure out. Okay. What's Ts? Okay, Ts is the time when the magnitude V out becomes 16. So that implies V out Ts equals minus 16 plus 16 E to the 500 over 3 Ts, and that equals the border voltage 16. That yields Ts equal 3 over 500 ln 2 seconds. Okay. At that time, the op-amp has to leave the linear region. So that's Ts, and at Ts, we see Ts equals, since between 0 and Ts, V out is 4 times Vc, therefore Vc Ts must be V out Ts over 4, which is 16 over 4. Yes, Ts equals 4 volts. So this will serve as our new initial condition, starting from the new initial time Ts. So at T equals Ts of n has to leave the linear region. Okay. So if it leaves the linear region, there are two possibilities. One is positive saturation region, the other is negative saturation region. And since at V out Ts, at time equal Ts, V out Ts equals 60 moles, that equation suggests that the op-amp is in positive saturation region. Now the question is, can it remain in positive saturation region for any interval of time? So let's figure that out. Positive saturation region. Okay. Now the conditions for positive saturation region is that V plus must be larger than V minus. V out is fixed at 16 volts. Okay. And due to that voltage divider in our circuit, if V out is fixed at 16 volts, then V plus is fixed at 1/4 of that, 4 volts. Now, the differential equation implies what? dVc plus 500 over 3 Vc equals 250 over 3, then times V out plus 8. V out is 16. Okay, you plug that in, and what we obtain is right hand side, 2000. Okay. Then we see TS is 4 volts. So we have the differential equation, we have the initial condition for the new initial time. So we can easily write VCT. That implies VCT, if op-amp is in positive saturation region, VCT has to be 12 minus 8 e to the minus 500 over 3 T minus TS. Okay, so let's call this equation 2. Now let's try to interpret whether that's possible, whether the op-amp can remain in positive saturation region. Now, this is VCT, and remember that VCT or VCT capacitor voltage is same as V minus. So VCT starts at 4 and it's heading toward 12 because this guy becomes smaller and smaller as time goes on, because now we have natural frequency negative. Okay. So it's instantaneous at 4, but just after that it becomes larger than 4. VC becomes larger than 4 means that V minus becomes larger than 4 because V minus and V plus V minus and VC they're the same thing, and then all of a sudden V plus is no longer or cannot be larger than V minus, okay? Because this is larger than 4 and this is 4 if op-amp is in positive saturation region. So that means the op-amp cannot remain in positive saturation region for any interval of time. So we have to go somewhere else. We are kicked out of the linear region, and it's turned out that we cannot remain in positive saturation region. So therefore there's only one place left that we can go, that's negative saturation region. Okay. 2 implies we see T greater than 4 for T greater than saturation time, TS. Since VC is V minus is greater than 4, that means V minus is greater than V plus, because V plus is fixed at 4 volts in positive saturation region. And positive saturation is not possible. So let's go to negative saturation region, therefore. Condition is that V plus is less than V minus, V out is fixed at minus 16 volts. That implies, due to the voltage divider, V plus equals 1/4 of that, minus 4 volts. Okay. Now, once again, using the equation that we obtained in the very beginning, equation 1, we have dVc plus 500 over 3 VC, this time equals minus 2000 over 3. Okay, first order non-homogeneous differential equation with a constant right hand side. This is differential equation. We have the initial condition, VCTS equals 4 volts. Therefore, we can write down the solution easily. So VCT must be minus 4 plus 8 e to the minus 500 over 3. That's our natural frequency. T minus TS. Okay. That's our VCT. And V out T is minus 16 volts. For greater than Ts, the time when the op-amp leaves the linear region. So let's sketch what we have figured out. This is VCT. And let this be the out. So at time t equals 0, both start at 0. And then what we have is, for a while, the natural frequency of the differential going on the circuit is positive. Okay, it's at 500/3. So what's happening is it increases. It tends to increase exponentially. Okay, for infinity. So for a while we increase. Likewise, the output also increases. Okay, this is the out is 4 times we see during that time, but eventually the out had to hit the border, which in this case is positive saturation reaching this border. Okay, it reaches 16, and then the time that corresponds to that is Ts. At that point, the capacitor voltage reaches 4 volts. At Ts. Then what happens? We consider the case whether the op-amp can remain for a while, at least at positive saturation region, and we saw that that's not possible. Okay, so the out cannot remain at plus 16 volts for any time. So what? And it cannot remain in the linear region. The op-amp cannot remain in the linear region. So we figured that the op-amp has to move to negative saturation region. So that means at Ts, the out voltage hit it minus 16 volts. And as for the capacitor voltage, this is what we have obtained. We started 4 at t equals Ts, and what we are heading toward is, now this thing is becoming smaller and smaller as time goes on, therefore VCT is converging toward that constant term, which is minus 4. Okay, so we were expecting a curve like this for VCT. Now let's check whether we have to do any further analysis, that is, whether op-amp can leave negative saturation region. So if you look at VCT, okay, so it becomes closer and closer to minus 4. It approaches minus 4 from above. Okay, so for at any given time, no matter how close it can be to minus 4, no matter how far, it can be very, very close to minus 4, but it will always be just a slight bit larger than minus 4. Okay, so VCT, and VC is V minus. Okay, so this V minus will always be slightly larger than minus 4, and V plus is fixed at minus 4. Therefore, this condition is satisfied for all future times. Okay, for T larger than Ts. Hence, the op-amp will not leave negative saturation region in the future, and this is the complete solution. Okay, so let's remark that, note that V plus will always be strictly less than V minus for T greater than Ts. Hence, op-amp will not leave negative saturation region. Okay, in our next example, let's consider a first order, well, a circuit that can reduce the first order circuit, this time with inductors. Example. we have three components connected in parallel. Two of them LTI inductors, and the one in the middle is piecewise linear resistor. 3 Henries, 6 Henries. This is I1. This is I2. Voltage is V. Okay. And the current of nonlinear resistor is denoted by I. Okay. By KCL, clearly, I equals minus I2 minus I1. And the voltage current relationship characteristics for the nonlinear element is given as following. Here the slope is given to be 4. And the slope here is clearly 2. This time voltage is the vertical axis, current is the horizontal axis. Therefore, slope gives us here this is the resistance. Okay. Or the unit of slope is ohms. Now here we have V equals 2I, and the curve can be described in the other region by V equals 4I minus 10. Okay. Now, for the initial conditions, I1 0 equals 3 amps, I2 0 equals minus 10, and we have to figure out the future values of I1 and I2. First, let's reduce this circuit to a first order circuit, which we can do because we have two inductors connected in parallel, and that we can replace by a single inductor, okay, whose inductance will be effective inductance. And for the case 3 Henry, 6 Henry parallel, that effective inductance is 2 Henry. Okay, so as far as this nonlinear or piecewise linear resistor is concerned, this parallel inductors can be replaced by a single inductor whose inductance is 2 Henry. So let's do that. We have this simple topology. This is the current and voltage of our nonlinear resistor, and this is our 6 parallel 3 equals 2 Henry inductor. Let's call the current of this new or equivalent inductor by I3. Okay, clearly I3 is minus I. And we're gonna deal with this circuit. We're gonna figure out I3, and then once we have I3, by voltage division, by current division, we're going to figure out I1 and I2, because I3 clearly equals I1 plus I2. Okay, so let's figure out the initial condition of I3. Since I3 is I1 plus I2, the initial condition I3 0 is 3 plus minus 10, and that's minus 7 amps. I3 0 equals I1 0 plus I2 0, which is minus 7 amps. So, we're now ready to begin our analysis. Okay. Since we have a piecewise linear resistor, we are expecting a piecewise analysis. Okay, So the first piece is for the time between 0 and t1. Well, t1 may or may not be infinity, so we're going to figure out that later. But initially, let's see what happens. Initially at t equals 0, I3 0 is -7, therefore I0 is 7. So that means this was 5, we're somewhere here, okay? So that's where we start. Okay, the current is 7 and the voltage is what corresponds to that. So I0 is minus I3 0, and that's 7 amps. Therefore, for a while at least, the relation between current and voltage is given by this equality, V equals 4I minus 10. Now let's write down the differential equation describing the evolution of I3. We have L di 3, and L is effective inductance 2. Okay, equals V. Okay, V3, and V3 is no other than V. That equals V, and V is 4I minus 10, and I is minus I3. Okay, and that's our differential equation. Let's rewrite it. di3 plus 2i3 equals minus 5. First order non-homogeneous differential equation with constant right hand side. We know the initial condition. I30 is -7. Therefore we can immediately write E as I3t equals minus 5/2 minus 9/2 minus 2t amps. Okay. Now that we have to determine whether something changes, okay, and if something changes in the circuit, then we have to change the differential equation. Differential equation changes means that the solution will also need to change its form. Okay, so let's figure out what's happening. So this is I3. It starts at -7 and it's heading toward -2.5. Okay, because this term will disappear as time goes on. The natural frequency is negative. Now I3 is therefore increasing from -7. It's going toward -2.5, and since I is minus I3, it starts the current of the nonlinear resistor starts at 7 and it's going toward 2.5. Okay, well, it's intending to go to 2.5. So what happens is we start here and we're moving in this direction. But we cannot reach 2.5 in that sense, at least, because in some time in the future we will hit, or I will hit 5 amp. Okay, it starts at 7 amp and it's going towards 5 amp. When it hits 5 amp, the curve changes character. Okay, from V equals 4I minus 10, it becomes V equals 2I, and that changes everything. That changes the differential equation. So therefore, T1, the time that something changes, is the time when the current becomes 5 amps, or equivalently, when I3 becomes minus 5 amps. Okay. So T1 equals 5. That means I3 T1 equals -5, and using the solution that we computed, we can figure out T1. So -5 equals -5/2 minus 9/2 e to the -2 T1. And from this equation, we can compute T1 to equal 1/2 ln 9/5 seconds. Okay. So I3 is this, not forever, but between t equals 0 and this T1. Okay. Now let's figure out what happens after T1. this is, let's say 7, and this is t equals 0, this is t equals t1, and let's see where we go from there. T greater than or equal to t1. Okay, so now the voltage current characteristics is given by this equation, V equals 2I. So let's use that to figure out the differential equation describing I3. L di3 equals V3, the voltage, V3 is V, and V is 2I. I is minus I3, therefore that equals minus 2I3. Hence, di3 plus I3 equals 0. That's our homogeneous differential equation. We have the initial condition. Okay, it's minus 5. Therefore, we can immediately write the answer. So I3 t equals I3 t1 e to the minus t minus t1. The natural frequency now is at minus 1. Therefore, I3t equals minus 5 e to the minus t minus t1 amps. Okay. Now let's see whether something else changes in the differential equation. Now I3 is from minus 5, it's now going toward 0. Okay, because we have no other term than the exponential. So I3 going to 0 means that from minus 5 to 0, it means that I from 5 is going to 0. And it will reach 0 exactly only at t equals infinity. Therefore, we don't have to worry about another change in our differential equation. So, our analysis is complete for I3. We have figured out I3 in piecewise fashion. But we were not asked for I3, we were asked for the currents that make up I3, okay? Namely I1 and I2. Therefore, finally, let's figure out those currents of the inductor. Okay, inductors in the original configuration. So, to sum up, I3t equals minus 5 over 2 minus 1 over 2 minus 2 t amps. For t between 0 and t1, and t1 is here. Okay. And it equals minus 5 e to the minus t minus t1 and for t larger than t1. That's our I3. Let's divide I3 between I1 and I2 now. I1t, I2t. So we had the following, the original configuration. This was I1, this was I2, and this was I3, okay? The opposite direction. And we have 3 Henry for I1 and 6 Henry for I2. Now, I1 of t equals I10 plus 1 over the inductance L1, and then you integrate from 0 to t V1 tau d tau. Okay. Now V1 is V, okay, because everything is parallel. There's only one voltage, so we have simply V tau d tau. And as for I2, the same thing. I2 0 plus 1 over L2 0 to T beta L beta. And putting this integral to the left hand side, we obtain 3I1T minus I10 from the first equation. From the second equation, we have 6 times I2T minus I20. Therefore, this equals I2T minus I20. So we know I10 and I20 we are given. They were 3 amps and minus 10 amps respectively. And also, by KCL, we have that I1 plus I2 equals I3. Okay. From those two equations, we can easily obtain I1 and I2 in terms of I3. Note that at this point, I3 is no longer unknown. We computed what it is. Okay, so let's call this equation 1. Let's call this equation 2. 1 and 2 implies 3I1 minus 9 equals 6I3 minus 6I1 plus 6, where we replaced I2 with I3 minus I1 in the first equation. So this now becomes only in terms of I1 and I3. That yields 9I1 equals 6I3 plus 69. Therefore, I1 of T equals 2/3 I3 of T plus 23 over 3 amps. Okay. And I3 minus this gives us I2. I2T equals 1/3 I3T minus 23 over 3 amps. So that's the final answer.